Dear students, in this session, let's see about an important optical phenomena, which is total internal reflection. And about this phenomenon, you might be very familiar with. For example, if you just see the glittering of diamond, you would have noticed this in diamond, the glittering is more compared to any other stones. Okay. And what is the reason for this glittering of diamond? That is due to this total internal reflection only. And you would have seen about these mirages when you just travel uh, in bus or car, and during the hot weather conditions, you would have seen when you just look at the road at a faraway distance, you would have seen that some sort of water appears on the road. Okay, that you call it as mirages. In Tamil, you say as cornel neer. Okay, so that is due to the total internal reflection only. And this type of images, what it is given in this picture. Here also, actually, this is it is a desert, and this place at the bottom is also, it is not water, it is also sand only. But here also, this is the condition of mirage only. Okay, in some cases, this is a common phenomenon, but in some cases you will have this superior mirages, which occurs where the image will be appearing at the top on the sky. So that is a very rare phenomenon. So that type of mirage, you call it as superior mirage. Okay, so the image of a very high building or something, or image of a ship on the sea, that will be appearing on top of the ship. Okay, so that type of mirages, you call it as superior mirages. So all these things are due to this total internal reflection. Okay, so what is that total internal reflection? That's what we are going to see in this chapter. So here, before seeing about this phenomenon TIR, let's have a look at this refraction of light. We would have learned in the previous session. So when a light travels from one medium to another medium, there is a bend, or there is a change in the path of the light while traveling from one medium to another medium. That phenomenon, you call it as refraction of light. Okay, so this takes place when it travels from air to glass, or glass to air, or from water to air, or from diamond to air, or air to diamond, or from any other substances, any other transparent substances, right? Okay, so in this, we would have seen the rules of refraction of light in the previous class also. So whenever this light travels from rarer to denser medium, this air, we know it is a rarer medium, and it is entering into a glass which is a denser medium. So when it is entering, we said there is a change in the path of light. If there is no change, then light has to take this particular path, it has to go this straight line path. So instead of going straight like this, it is taking up a bend. There is a bend in the path. So this, I told in the previous class itself, this bend may be either towards a normal in this direction, or it may be in this direction. Okay, so but here, whenever light travels from a rarer medium to denser medium, the refracted ray moves towards a normal. So you have to draw like this. So that is the rule number 1. Okay, so always the refracted ray will be bending towards the normal. This is rule number 1. So you have to remember this clearly, only then you can draw the ray diagrams easily. Okay, so the same way, when a light is traveling from a denser medium, see, glass is a denser medium, and it is from glass, it is entering into a rarer medium air. So here, what happens, this is the normal. Normal is a perpendicular line drawn at the point of incidence. So here, instead of moving here, it has to go straight like this, or it can just move towards in this direction. But instead of moving like this, it moves away from the normal. It is moving away from the normal. So that is the rule number 2. So they bend, the refracted rays bend away from the normal when a light ray is moving from optically denser medium to a rarer medium. So when it is moving from a denser medium to rarer medium, the refracted ray will move away from the normal. Okay, so this condition will be applying in total internal reflection, right? Okay, now we just consider this particular case. Consider this is object O is at this point. Consider this point is object, and from the object we are going to consider the different rays which are coming out in different directions. Let us consider this N1 is the refractive index of this medium. Let it be water. Okay, and this N2 is the refractive index of air medium. So here we are taking light is traveling from water to air medium. It means it is traveling from a denser medium to rarer medium, right? Now, first we'll take this particular ray of light. Okay. So when you take this particular ray, it goes straight. It means what? It meets the interface. Let XY be the interface between the two media. It means what? Interface in the sense it is the surface of separation between the two medium, water and air. Okay. So here this particular ray that is traveling straight, it goes normal. Okay. So we know that a ray which is falling normally on the interface, it goes without any change in the path, so it travels like this. Okay. Now you consider another ray which is striking at the interface and making an angle theta 1 with the normal. So here theta 1 is the angle of incidence. You know, theta 1 is the angle of incidence here. Okay. And here this theta 2 is the corresponding angle of incidence, angle of refraction for this theta 1. Okay. Now just in case if the angle of incidence is increased further, for example here this is another ray where the angle of incidence is increased further, then what will happen? The refracted ray also will move away from the normal only. We said light is traveling from denser to rarer. So that is why we have drawn the refracted ray which is moving away from normal. So here in that case you can consider if the angle of incidence is here theta 3, then its corresponding angle of refraction is theta 4, it increases. So here you can say as the angle of incidence I increases, we have seen that the angle of refraction R also increases. At a particular angle of incidence I, for example, that you have taken to be angle of um, incidence I, we are marking it as theta c, and for that angle of incidence you see here the refracted ray is just grazing the line of separation between the two media. So it means what so this for this particular angle of incidence, let me take that particular angle to be theta c. For that angle the refracted ray just grazes the line of separation between two media. It means the angle of refraction becomes 90 degree. And still if you are increasing the angle of incidence, just in case if the angle of incidence is greater than this particular value theta c, if it is more than that, in that case what happens here, this is the condition where the angle of incidence is greater than the critical angle. In that case what happens, and what is the condition? We have seen the refracted ray should move away from the normal, and here already it was in this position. Now moving away from the normal means now the refracted ray takes up this angle. So here it means what? The incident ray which is striking at an angle more than the critical angle. In that case the ray is not refracted, it is reflected within the same medium. So here we say reflection occurs instead of refraction. Okay, but here also light ray is moving from one medium to another medium. Normally when a light ray moves from one medium to another medium, refraction should occur, but here at this condition instead of refraction the light is reflected back into the same medium. So this phenomenon you call it as total internal reflection. Why this name total internal reflection? Because whenever light falls on certain medium, a part of the ray will be reflected and part may be refracted and something. But here in this case, whatever is the amount of intensity of light falls on the surface with that particular angle, that intensity of light is totally internally within the medium, it is reflected. So this phenomenon you just call it as total internal reflection, right? So we'll see this explanation in detailed form. Okay, that is here you just consider as I told you, this is the ray which goes normally. So when a ray which falls normally on the interface xy, we know if the angle of incidence is 0, so angle of refraction is also 0 in this case, right? Okay. Now if we are slightly, for this particular ray the angle of incidence is slightly greater than that, it is 20, and the corresponding angle of refraction it finds out to be 27 degree. You can find out using what to say Snell's law also, you can measure this. Okay, and here you consider this case angle of incidence is slightly increased, it is increased to 30 degree, and the corresponding angle of refraction is found out to be 42 degree. And still more in this, for this particular ray if we measure for with this normal it becomes 40, and for that the angle of incidence becomes refraction becomes 59 degree, and still more the angle of incidence is increased. For a particular angle of incidence, the refracted ray just grazes the line of surface between the two media. It means here the angle of refraction is equal to 90 degree. So that particular angle for which, that is here in this case, the angle is 48.8 degree. Okay, so here for water, when a ray of light is entering from water to air, the critical angle you call this is actually 48.8 degree. So this angle for which the refracted ray just grazes the line of separation, or you can say for which the angle of refraction is 90 degree. So that angle you call it as the critical angle, right? So critical angle is what? It is the angle of incidence in the denser medium. Here this is the denser medium. So critical angle is the angle of incidence in the denser medium for which the angle of refraction becomes 90 degree. Okay. So that angle you call it as the critical angle. And you see here, for any ray which is incidenting on the interface with an angle greater than this 48.8, which is greater than this critical angle, if the angle of incidence is greater than the critical angle, then there is no refraction occurs. The ray is totally internally reflected. It is reflected within the medium. So that's what this phenomenon you call it as total internal reflection, right? Okay, so we can define this critical angle. At a certain angle, the refracted ray follows the path exactly along the surface of the denser medium. It means what we say, that is what we say, the angle of refraction is 90 degree. So that angle, you call it as that angle of incidence in the denser medium for which the angle of refraction becomes 90. That angle, you call it as the critical angle. So here, let's see what are the conditions for the total internal reflection here. The first condition is light should travel from denser to rarer medium. It means the light should travel from denser to rarer medium. So that is the first condition. Okay. Why is it so? So when you just take consider this is a incident ray, and you know this is the line drawn at the point of incidence, you call it as a normal. Okay, and you consider this is the denser medium and this is the rarer medium. Only then the refracted ray will move away from the normal. Okay, so in this condition, so when you just increase the angle of incidence, the refracted ray will be moving like this away from it, and finally it grazes, then it comes inside this. Okay, so it for this condition to occur, the light has to travel from denser to rarer medium. If it is from rarer to denser medium, the light ray will be moving away from the normal. So this condition may not happen. Okay. So second point is the angle of incidence in the denser medium, that must be greater than the critical angle. Even it must be slightly greater than the critical angle. So these two are the conditions for the total internal reflection. So what is the condition? The ray of light, it should travel from denser to rarer medium for this total internal reflection to occur. Second condition, the angle of incidence must be slightly greater than the critical angle. Okay, so this you have to remember. Then we'll see, actually this relation we'll see in the next session, and there are certain examples of TAR. I said no, this is that is the diamond. The glittering of diamond is an example of this total internal reflection. Here, actually this diamond has got a refractive index is very high. So since the refractive index is very high, its critical angle will be very low. So whatever is the ray which is entering into the diamond will not be coming out of the diamond easily. So that will undergo reflections at various phases of the diamond, and it glitters more. So we know that a diamond which has got many cut faces will be more glittering than the ordinary diamond which is taken from the ground. Okay, so that is why we say polishing the diamond or cutting the diamond. No? It means for at the various phases the reflection will be more. Okay, and in medical field and in the field of technology also we make use of this. So in fiber optics, it has become a very important thing. For example, when light ray which is passing through this fiber, what happens, it will not be coming when a ray which is entering into it, it will be internally reflected like this. Again it will be internally reflected at the various phases like this. So it will not be coming out of the fiber, and it undergoes various internal reflections, and finally when it is coming out of it, it will be more bright. So that is what is happening in this case. In all the fibers, when the light which is coming out of it will be more powerful, because within the ray it undergoes multiple total internal reflections. Okay, so the same technique we make use in case of medical field, in case of endoscope and all. So when you send an optical fiber inside the thing, the intensity of optic light which falls on the organs, inner organs, will be more, and there you'll be having a camera to see the objects more clearly. So these are the applications of total internal reflections.